There's a really cool weld in submarines that passes through a bulkhead that a dude actually has to weld in a mirror behind him is the only way to get to it. There's like 2 dudes in the world that can do that. And they make like $2,000 an hour. All right, welcome. Let's talk welding. One of the first spots we go as engineers for anything is not just what does John think or Stefan think, but what does code say? So a list of a lot of different welding codes. There's ASME, which is more centered around pressure vessels and piping and process piping and those kind of things. And then there's the American Welding Society, which got together around 100 and something years ago and has written tons of different codes and standards to help us. Some of the important ones are here's how to do the actual symbols, here's how to do welding terms. And then the ones we are most familiar with, D1.1 is for how to weld steel and make good weld metal. 1.2 is aluminum. 1.3 is sheet steel. If you're taking the P exam, you may have to deal with 1.5 for bridge welding. Stainless is 1.6. We use that quite a bit. And then there's a couple of others in here that every once in a while come up or are kind of cool to do. There's some in the 14s. Crane welding for mills, there's one for that. Let's talk weld symbols for a minute. Hopefully you guys are throwing some questions for me in chat. There's a super cool thing that was put in here for weld symbol references. This big bad boy that looks super confusing is right out of AWS, and it's 2.4. Remember a second ago we said that was the standard for all symbols for welding. Just to look at it really quick, this tells you what and where to put everything in your weld notes. The arrow points to something. Our circle is all the way around, which we use way too much. The little flag as you do this in the field. There's different spots to put links and sizes, and then there's always a tail where you can put any notes, extra stuff, and things like that. Sometimes you'll also see a continuation of the arrow, and they'll call out NDT or testing or things that are specifically called for that. Can somebody pull up Solid Edge for me and pull up the draft pack, and let's look at that weld note thing in just a second. Let me know when you got that up. While he's working on that, and actually let's go through this document, because this pulls a lot of cool stuff out of 2.4 and 3.0, which are the 2 AWS standards. There's different types of callouts for welds and how things might be done or finished. This is a really, really good thing pulling out to explain what the arrow actually means. So if the symbol is above, it means other side. So that would, if I put the arrow here, that would say this other side is welded. Whereas if the symbol is below the line, it means arrow side. So there's the weld, right? And a lot of times the little weld symbol looks just like the weld does. So you might have, we'll look at that, different types of welds in a minute. Field weld is your flag. Circles are all around. You have to be careful of all around because you may not always want all the way around. You may only need a couple of welds to hold load, so saves the guy some welding. Now, in architectural cases, you often have to weld all the way around to seal it and keep water out and make it look nice and all those kind of things, right? How do we get around that? A lot of times in architectural stuff, we say fully welded connections, right? They're just going to weld the shit out of it anyway. And we'll talk about caulking in a minute. There's other cool spots in here. I would take a moment as you can to go back and read back through this for different types of welds and what all the symbols mean. Everything from intermittent. Intermittent welds come up a lot. Stefan and I seem to always be talking about them. 2-6 means there's 2 inches centered every 6. So how far apart are the welds? Edge to edge. Trick question, quick. We have finish symbols that you can add on. So you might want them to over weld a little bit, or you might want them to grind it back out, or you might want to see it smooth. You'll see this smooth or ground flush a lot of times in architectural stuff because you don't want a big nasty looking weld on your joint. You want to be able to finish it and paint it and it look pretty.
Is that something that we would call out, or they can just do to make it look nice?
It depends. It depends on what is needed. And I'll get to that in a minute as to what our role is and those kind of things. But the point is there's a very clear way to describe exactly what's going on. And the second part of that is the welding shop may not always know what that means. So you might have to do some education. We'll look through a couple other things. We've got different types of welds. We have unequal leg welds, which we don't use a lot. Groove welds. The arrow always points to the side that is prepared or prepped. I'll show that here in a minute, hopefully. Some of our joints, when we're doing full penetration welds, may require backing. or putting extra pieces in, or doing a root pass and then coming back later and clearing it back out and putting in weld metal. We can look at some of those things in a minute. There's all different types of welds and symbols and things like that. There's also adding in surfacing, which you see a lot in vessels and linings and things like that wear. They'll just come in and weld a whole bunch of material to sacrifice to use for the product later. Spot welds we don't see a lot. Those are more in automotive. Stud welds we do quite a bit of. There's actually a full AWS standard for stud welds, and there's a big section of the AWS D1.1. And then even in this, there's some practice exercises and a cool drawing that I don't feel like rotating right now. Cool. Brian, you want to share the screen for Solid Edge for a minute?
Yep.
So in it is the weld symbol, and notice it's all those same boxes you just saw at AWS. Do the little drop down for the fillet weld there.
This one?
Yep. So there's all your different types of welds. You can put lots of things in the tails. You can do all arounds. You can do it both sides. You can stagger. Basically, one of the cool things about Edge is you can do any damn thing you want, and the weld symbol thing is very robust. One trick, if you open a weld and hit escape and then start the thing again, it will redo the last weld that was in there. So if you're switching back and forth between, you got a bunch of fillet welds and then you got a bunch of flare bevels, you can go back and forth, open the last one, and then you'll be able to do that one again. Does that make sense what I'm saying? So that way you don't have to recreate everything from scratch. Once you get one cool weld in, you can use it over and over again. So yeah, just do some of the drop downs and stuff there. Yep, so you got that. What's the one right above it? And it should call out what things are. So if you're looking for, go back to the little fillet weld symbol there. Fine. Come on down for the triangle. Give me a triangle. There you go. Click that. And if you hover, it'll tell you what type of weld. So if I tell you to do a flare bevel or a single bevel or a double bevel, all these kind of things are called out and described. There's the compound bevel. There's a flare bevel with a reinforcing fillet. So click that last one.
This one? Is it this one?
I mean, I'll let you guys, as an academic exercise, figure out what's going on. You can stack welds on top of each other. You can stack NDT on top of each other. That's a single-sided bevel weld with a reinforcing fillet. Pretty cool, right? So you can do anything you want. That 1/4 inch, you would probably move down to the box below for the size of the fillet. And then you would not have the 1/4 inch if you wanted a full flare bevel. All right, so there you go. There's a cool way. Single side flare bevel, prep the arrow side that I'm pointing to. So if we were on a joint like that and the arrow is pointing to this side, that's the side they would prepare or make the bevel on. So your arrow points to the side that gets prepped. And then you can do all kinds of things behind it. Now, if you wanted to add RT and other things on it, when you have that weld note on, you can actually do another weld note, click that weld note, and add a line on it in Solid Edge. I won't go too much further there. I will steal back. I just wanted you guys aware that all of that stuff is there. Okay. For design, I encourage every one of you to order all of these old books or find them in some manner. Blodgett wrote a lot of really cool, and he was sponsored by Lincoln Electric. Yep, Farn's got one. Really, 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 really good book. This is an old school book, so I encourage you just to read it for fun. You get to see all cool things like how they test stuff, how they break things, how they put stuff together. There's a lot of old charts and graphs and things to show you what's going on. This stuff's even older than me and John.
That's old.
Right? All right, let's talk welding of steel. The D1.1 structural welding code for steel. The important part in any code or standard is immediately go to what's the scope and what are the limitations. This code was specifically developed for welded steel structures with carbon or low alloy steel that are an 1/8 inch or thicker with a minimum yield strength of 100 KSI or less. High strength material doesn't apply. Thin ship doesn't apply. If it's sheet, it's 1.3. If it's aluminum, it's 1.2. If it's stainless, it's 1.6. If all of these apply, this is the standard for it. Now, what this standard was written was to help you make good welds. So if you follow this standard to the letter, you make good material. And in some cases, you don't even have to test your procedure, your process, or your people. You'll know you make good welds. Okay. So limitations are here. 1.4, engineer's responsibilities. The engineer shall. What shall mean? Must, right? Should is you oughta, shall is you must. responsible for your contract documents and telling people what to do, what codes are required, what NDT is needed. If a thing needs to be MT or MAG inspected, you've got to specify that. What your acceptance might be if it's anything other than something I'm going to show you. If it's fatigue and you need toughness standards, basically you've got to tell people what you designed, right? You've got to communicate your design intent and what is needed. Keep going. In 2.3, it talks about all the different things that need to be in your plans. Like you actually need to call out the welds and their length and where they are and stuff like that. So these are things, if you get in an argument with somebody about what you need to put in there, well, here you go. There's 2 spots to go, right? IBC tells you the loads and things you got to put on the document. And this tells you what you got to put in for welding and specification. There's a lot of little cool things to read in here, like fillet welds are described here, effective lengths. Here's the one I bring up a lot of times. Intermittent fillet welds have to be at least 1.5 inches. Otherwise, you make a zipper. You've heard me say that over and over. Here's where it came out of. Minimum lengths of welds have to be certain sizes in comparison to the components and the weld size that's in there. All this stuff is in there to help you. There's a really cool table here in 2.5 that I like to look at a lot. It's talking about fatigue, and it's got some things to help you if you're designing a joint for fatigue, but it also tells you where the high stress is going to be. And it's really cool for me if I'm doing a real complicated joint, I might pull this up and go, well, does my FEA pattern match what I should see here? And if it does, cool, maybe I got my loads and constraints in correctly.
You back up to where you were showing the effective length, effective size?
That was 2.4. 2.4 had some fillet weld stuff. Each type of weld has a different section for that, John. So it's back in section 2 is for design. So just read section 2. Cover
the reason I was asking you to go back, somebody asked a question in chat that points to that section. So whatever that section is.
I'll come back to it in a minute. Here you go, maximum fillet weld size. You know, we always have the little rule of thumb, 1/16 less than if it's 1/4 inch or thicker. AISC borrowed it from AWS. They did it because they broke a bunch and figured out what cracks and what doesn't and decided what actually makes good weld. So a lot of these things that we hear often are rules of thumb are straight out of here. Figure 2.1, did I already show that one? Yeah. Maximum fillet weld size. 2.5 is a cool one. So when you're welding something together, you don't always want to run out to the end because that little corner right there creates a stress concentration. So a lot of times if you slap a plate on the beam, you don't do a weld all around, especially if you've got fatigue loads, because you started a crack right here in this little corner. These things are, you'll put in your weld node a hold back. Hey, give me 4 inches of weld, 1 inch hold back on each end. That way I don't create a stress razor or a stress concentration. Same thing on the turnbacks for angles on a fillet. If I just weld the one side, well, I've got cracks already started. I got to turn the corner a certain length to keep from having and to make my connection flexible. So again, highly recommended cover to cover. I just showed what, don't tie the welds together. Got it? Cool. All right. I know I'm moving fast, but I'm going to keep going. All right. Section 3. There's 2 things you got to do to have a good weld. One is you got to have a procedure that makes a good weld. That's what section 3 is. It's a WPS, how to make a good weld. And I'll show you an example of a written up one in a minute. I'm just going to skip ahead to the tables, and we get in these a lot. Approved base metals, what can I weld and what groups it in? That helps me then determine in 3.2 what fillers I use. So if I'm welding group 1 to group 1, I'll use that. If I'm group 2 to group 1, I might do something else. But these are all the recommended fillers for different types of materials. A lot of times we weld A36 to A500, right? They're not necessarily, these are in the same group, A36 and A500. So grade C and less than 3/4 A6 are in group 1. So I can use a standard filler of an E70 if I'm sticking, or a F7 if I'm doing submerged arc. There's some other cool tables in here. I show these with Stefan a lot. Interpass temperatures. So if I'm making something in the field and it's January in northern Colorado, I probably need to think about, do I need to mention preheat in my notes? If I don't preheat a joint, I just start welding, I can end up with cracks in my weld because it doesn't, it's a quick or a fast cool or vice versa. So these are guides for different types of materials and different categories and sizes for different types of welding processes. Stick is the little sticks you see sometimes in the field. Most people now are using flux core or MIG in some capacity. You can put down about 3 times as much weld flux core as you can stick. The only problem is your welders have to be a little bit better. And just for instance, if we were MIGging A36 that's 1.5 inches thick, our minimum interpass and starting temperature needs to be 150 F. So if I'm welding in Idaho in January, I need to mention that in my note for when I design it. Make sense? If I'm welding, if I know it's going to weld outside in June in Florida, I could probably care less. It's probably 200 degrees outside, right? Minimum partial penetration weld sizes based on base metal thickness. So we were looking at this a little bit the other day, right, Fawn? We were trying to figure out how deep to make that joint. Well, we had to make it. It's 1.5 inch plate. It needs to be at least 3/8. Or we probably made a zipper. One of the reasons I pushed you guys to 3/8 is I was over there looking at this table.
Is that 3/8? It kind of leads to my question, but how do you know if that's going to be a multi-pass to clear that 3/8?
I'm glad you asked. Maximum fill pass thickness, maximum single pass fillet weld size, maximum root size by weld type and process. So if I am in a horizontal position fillet weld flux core, I can weld up to 3/8 in one pass. MIG or flux core. Most shop welds are now done in one of these two processes. Field welds oftentimes are done stick. So you just look between the two. If I didn't know what they were going to use, I might use a 5/16. Well, how do I know what position it's in? I'll show you that in a minute. But this gives you an idea. I'm constantly looking at this when we're trying to figure out welds because I'd like to do it all in one pass if I can. Otherwise, I put in a lot of heat. And the other thing is when I come in for the second pass, I actually have to grind out a portion of the last pass to make sure I have good weld sound weld material, and then I can make my next pass.
Even for the gas one?
Yes.
Or does that just stick?
It's for all.
Interesting.
You'll chip or clean or prepare your process. Let's see, pre-qualified. And this is for pre-qualified joints. You can do others, but you're going to have to write a procedure, have someone weld it and test it for it to pass D1.1.
Is there a separate table for GTOL? I just see everything but.
You normally are not TIGging steel. TIG will be on aluminum or stainless or titanium. Now, sometimes like in piping, you'll have a TIG root pass, but when they come back and fill everything in, they'll grind that back out and then backfill it on the backside. Good question, though. Let's see what else. 3.2, figure 3.2. Okay. So this I pull up a lot and look at you guys with, and extremely important. There's not a lot of different tables. There's one version in inches and exactly the same, but in millimeters. So there's not 37 different joints. There's some shown twice. Make sense? And what this tells you is how to make a good weld. So if I wanted a square groove weld MIG process, I can weld 1/8 inch with these parameters and this note and make a good weld. So can I butt weld 1/2 inch plate? No, because I have a 1/4 inch max. And if I wanted to do that, I've probably got to come over here and create a better full joint with backing. See, this goes to unlimited thicknesses. I can stick unlimited, 1/4 to unlimited with a backer and make sound metal. Or I could do this where I can butt, but I have to back gouge. I can do up to 3/8 max with different processes here. Now, how do I use this? Call somebody like me to help you, right? Until you get a feel for them. We never see this, right? Flare bevel, joint to joint. This gives you all the minutes. Let me get out of millimeters, sorry.
Never seen it in my life.
This is how to make good welds. So it's a great guide to go. And the really cool part is if it's a shop that is AWS certified, you just put this in the tail and you don't have to put anything else. You tell them, give me a BP11 GF, and they will know to do this because they already have this process written up in their shop.
Normally, I just leave them blank.
What's that?
Normally, I just leave them blank. So we should be putting like BP11 or something. Or
Well,
I guess
you don't
it
have
depends
to.
on what they're using.
You could put the whole note in and everything and all the requirements. Or if you know they're a code shop, you can just put that in the tail and then everybody knows what's going on. It's a good way to call out a specific joint. Hey, let's just do a BP1 lowercase b. All right, well, that's a double-sided partial. Cool.
Yeah.
I'll keep going. We could spend the rest of our life there, right? All right. Now that we have a good joint, and I'm going to go a little long. Now that we have a good joint, we have to make sure the welder can do it. That's chapter 4. So the welder themselves has to prove they can make good weld material. And what you'll do is you'll have them weld different things. So this was what we were talking about a minute ago in positions. This is flat. This is sitting on the table. It's very easy. This is overhead. It's above your head. It's a pain. You're dripping weld metal on your back. So if you go back to that table and look at them together, the joints are a lot more controlled for overhead and vertical than they are for flat. I can weld flat thicker in a bigger single pass than I can vertical. So these are things to think about when you're designing a joint and how they're going to put it together and talking to your shop. How are you going to present it to your welder to make sure that they can make a good weld? And if they got to flip it 75 times to get it in flat position every time, maybe you could have designed the joint differently. Good and confused? What'll happen is you'll get your welder to weld one of these, and then you'll go break it. So you'll have him weld this plate like in this position, and then you'll send it out for these different tests. And if he passes all of them, then you go back to another table to see what positions he's now qualified for. Here's another test plate that you'll use sometimes for your welder. This one's a little more pain. There's a big root opening, right? But if he passes this, he gets paid a lot of money to weld pressure vessels from now on. Here's the simplistic one. You just weld a fillet and break the piss out of it. And if it breaks in the weld, then he made a good weld. And if it breaks outside of it, he sucks. And he's got to come back and do it again. Everybody good and confused? So as you're doing this from scratch, what you'll do is you'll figure out what joints you're going to need. You'll write a procedure for how to make the joint. You'll have your best welder welded in a certain position. And now your shop is qualified to make that weld. And then they just get more welders to weld to be qualified for that procedure. I know that sounded confusing, but it's actually pretty basically just chasing out paperwork and making sure people can make good welds. To keep rolling, because I'm running out of time, Fab is a really good one to read, and it takes out a lot of arguments. Because if your shop is giving you about your design, you can pull this up and go, bro, you were supposed to do this. Like, this is how you attach backing. This is how you do preheat. This is how you were supposed to control your variables. This is how your environment was supposed to be controlled. Hey, minimum fillet weld sizes. You were supposed to follow this table. I'll look at a couple of these. You have minimum fillet weld sizes. We'll pull that table in a minute. Weld profiles is 523. I'll show that in just a second. Where's 23? There it is. So for different types of welds, we have different profiles. I'll show this to you and they'll make more sense. Repairs is big. If you remove or do certain things, you're limited in how you can do those. Like you can't just go torch shit out and turn my material to shit. You got to follow some procedures. And then my favorite section, you guys have heard me and you thought I was joking. It's actually called caulking when you just weld it to seal it and make it look pretty and not actually have a structural joint. So, you guys have heard me say, are these guys welding it or are they caulking it? Because sometimes we're trying to figure out how much load we can pass through that joint. And if they're shady, sketchy, and it's aluminum, they may just be like literally just covering the hole. And we might not get a structural joint out of it. We might have to add some material or add something. That makes sense? Let's see, tables. I needed 5'7". Minimum fillet weld sizes right here. So if I'm welding half to half and I call it an 1/8 inch weld, doesn't meet AWSD 1.1. Needs to be a little bigger. Figure 5'4" is used in a lot of different spots. This used to be one simple figure. In newer versions, it's more convoluted with all the different types of welds. The important thing is here, dude's got to make you a weld without a ton of reinforcement, which causes stress concentrations, without a bunch of underfill, because I don't get my full joint capability. And there's desirable and undesirable profiles. One of the things when you inspect a joint is, does it meet these profiles or not? I'll show you that in just a second. So if you come out and you look at your fillet weld and there's a big gouge in the middle of it like that, that's unacceptable. Get back to welding. And follow the repair section, which says how you have to take the old weld back out and put the new weld in. This is the most important section because of our friend 6.9. When we say welds must be to AWSD 1.1, what does this say as a requirement? All welds shall be visually inspected and shall be acceptable in 6.1. or if they're tubular, this other table. All that's got to be satisfied. So if someone gives us into about something at the D1.1, the first question I'm going to ask for is, give me your visual inspection record. Oh, I don't have one of those. We didn't look at it. Well, then you didn't weld it to D1.1 because it's required that you visually inspect every single weld. It's a good out for us. Let's go look at the actual table. No cracks. Who would have thought, right? Actually got to be fused together. Sometimes you'll see a cold lap where your weld is sitting on top of the material and didn't actually fuse into it. Crater cross sections, weld profiles, I told you about. It's got to meet those acceptable profiles. Certain processes and materials that have to be within a certain time of the weld or after a certain time to see if cracks form. Can't be undersized, can't have undercut, can't have too much porosity, all those kind of things. I'll show you some scary on that in just a second. Do they have to do NDT? If you require it. Remember earlier, the engineer had to tell if NDT was required or not. Sometimes you'll see me ask for someone to mag or UT a joint just to make sure I don't have any cracks in it. If it's something critical or hanging over somebody's head or it's going to be fatigue loading. Cool. I'll breeze through the rest real fast and we'll be done. Chapter 7 is all stud welding. We do a bunch of that stuff, right? And there's some other standards. AISC has stuff. John has a lot of cool resources on that. Section 8 is repairs or strengthening and repairing of existing structures. It's various things they have to follow to do there. Cool read. Chapter 9 is all tubular structures. We do a lot of those, right? And then the worst of the worst are fatigue-loaded tubular structures because those joints are very tough. Normally, these are going to require bigger welds and a lot more NDT. There's some cool specifics back here on types of joints. There's those cool tables we showed a minute ago with stress razor areas. There's a lot of different discussion of positions and how things go. There are some cool pictures back here to think about how joints come together. So when you guys call out all this bracing, doesn't always come to that point. I've got to figure out how to then weld that. And do I have enough room for the material to all fit in there? Same thing when I'm necking up or transitioning or necking down. A lot of cool things to think about how stuff comes together with round and square joints. Like they've got to cut that and then slide it in place and then weld all the way around. It's not a straight joint. Same thing when things are going in and out of sleeves. There's a whole discussion of how to calculate your punching shear in some of these tubular structures, which is back in the thing. Here's a big one that you see a lot of times. When we draw it on the page, it looks simple. This is what the guy actually physically has to do to make this happen sometimes. It's an overlapping K. A lot of different things to consider. Here's the weld profiles for tubular. There's thoughts of how things come in at different angles. And then my favorite picture in the whole book, 6G and 6GR. If you can weld either one of these joints, quit now. You'll make $500 an hour welding for the military making submarines. This is a full angular pipe, often up to a foot in diameter, above your head with something in your way. If you can make that weld, amazingly, you're qualified for every other weld in every other position. It's super expensive and very few people on earth can do it. But if you have a really good dude and you get him qualified 6G, he can literally weld anything. There's a really cool weld in submarines that passes through a bulkhead that a dude actually has to weld in a mirror behind him is the only way to get to it. There's like 2 dudes in the world that can do that. And they make like $2,000 an hour. All right, to finish out, there is an annex. I will call your attention to a couple of things. In here is the annex. There's a really cool spot here talking about what the actual effective throat is in different welds and how to calculate it. So if you're doing some really detailed stress analysis, sometimes this will help you with some of those dimensions because you can lay them out in CAD pretty easy. 493, I called attention to. Let's see what it was. This is an actual procedure. So a minute ago, we were talking about a weld. You actually draw up exactly what it looks like. So this is a double bevel groove full pin with backing. This tells you the materials, their thicknesses, the process used, and the different passes. See how it's multi-pass? The first pass is going to be flux core and a 4G with this filler and these temperatures. 2 through 8 is going to be this. This is a 16-pass weld. That's probably what they're going to have to do for those 4 plates for contract fab foreign and why I was trying to get it down to a 1-pass weld. 1.5 inches, they'd have to do something similar to this, right? After the annex is the commentary. And I highly recommend if you're doing something in particular, you get back there and take a look at it. So here's the whole commentary. It's just like ASE. It's got a lot of cool in there. One I do call attention to is C5.23 in Fab. They will actually tell you where a lot of this came from. In 82, we did this, and this is why we did it. And then we figured out, wait a minute, that probably wasn't right, so we redid it. You'll see that a lot in the commentary of codes. They'll actually tell you what's going on. ASC 7 is really good about that. Hey, we were wrong. That's why we just changed it. So I encourage you guys to go in and take a look and read through the commentary. In some cases, here's a whole discussion of caulking. And then I have one final C6.7. Where's 7? Oh, I think it's a picture. Yeah, here it is. Okay. Here's the scary one to leave you with. Remember the visual inspection? If you read down through it, there's a certain amount of porosity and flaws that can be in a weld and it still pass. These are all acceptable welds. They have holes, start stops, porosity, etc. in them. So just because you designed the perfect weld doesn't mean it's going to be perfect. And this is why I highly encourage, and I do all design of welds with base metal material strength only. I don't give any credit for the stronger filler. And this is why I use really high factors of safety, because I know I'm not going to get perfection in the field. I'm probably not going to have it inspected. They're probably not going to write a procedure, right? So cover yourself and the people that are using the things that you're designing. Make sense? All right, that's all I got. Questions?
You're all in chat.
See if I can answer these. How do you know when a weld is too long, going to cause warping or whatever needs intermittent welds? Normally with steel, you don't have to worry too much unless it's thin stuff, and 1.3 will give you information on how much you can do in a pass. The one you have to worry about is stainless. Stainless is called the galloping material. It will move all over the place on you. What you really want to do is find shops that weld a lot of stainless and ask them, what order should I go in? Should I put a backer on it? Should I put a bridge across to hold it in place while I weld it? Those are all things you need to work with your shop. I don't think we know enough to know that. If you're really worried about it, we'd bring in a welding engineer. Some part of the weld call is not specified. Does that mean it's at discretion or it's not permitted? It's not specified. So if you don't give them information, they're going to do whatever they want. So if there's something you want, give them that information. So for instance, on pipe or on a railing, we're like fully welded connections because we know they're going to caulk it all together and the load's not very high and we don't care. But if we were making a tubular structure like a tower, now we're going to get care. Now we're going to call that weld out. Now it's a flare bevel with a reinforcing fillet, and it's got to be inspected and it's got to be magged. So control what you need to control. If you don't have to control it, give them liberty. It's not fatigue loaded. Just doesn't need to look pretty. Just stick it together, bro. Are there different calcs used for non-fillet welds? Is there a good reference for that? So you saw the little chart that showed effective throat. Shear is going to get to the effective throat in the same manner no matter what. So from us ME stress people, we now know how to handle that. For you guys, you probably got to find a different table, right? John may can answer that one better than me. Pros, cons of multipass. I mean, every time you start back over, you can add a flaw or an inclusion to the weld that can decrease its strength. And it's more time, more money, more expense, and more chance of warping and things not fitting up well, right? So like that weld a minute ago with 18 passes, if I needed that perfectly flat, I'm probably going to have to put in some stiff backs and things while they're welding it together. Amy says, sometimes drawing a fillet weld symbol with no weld size, what does that mean? It means all the people involved don't know what they're doing. Because if you're designing it and it's AWS, the engineer has to call out the weld size. A fillet weld has to have a size because it's non-implied. If I don't put a dimension on a groove weld, that implies full pin. But a fillet weld doesn't exist without a size. The problem is CAD jockeys, especially in AutoCAD, the first symbol that would pop up in a block was a fillet weld. So everybody just threw it in and nobody put a dimension because nobody knows what it means. They're just like, weld it. Which is cool if I'm making railing or an awning or something. But if I'm building a structure, like we have a really complicated mega structure I just bid, we're going to spend a lot of time and probably hire a welding engineer. It just means people don't know what they're doing, and that shop probably is not a code shop. References for stacked reinforcing welds. That's a really good one, Trey. Normally what I do there is just look at them independently as to what share of the load they can each take. And I think if you're conservative enough in your weld calcs anyway, that should get you in the neighborhood. Let's see, John says buy all the books. Are they really only $20 right now? That's awesome.
I just looked. They're 25, 17, 50, and 5.
Dude,
5 is the solutions manual where they go through and do weld calculations for 40, 50 pages.
I have 3 or 4 projects over the years that there's no way I would have been able to done without Logic. I would have just sat there for the rest of my life trying to figure it out. So when you're hosed, just flip through Logic. What would you call out for not welding at the corners look like? A note that says no weld. If you want the hold back, you put that in the notes and you'll put a little dimension. You'll put in like 1/2 inch hold back, or you'll put that in the tail. 4-inch weld center, 1-inch hold back each end. Just if you can read it and understand it, they should be able to also. When you use a universally fully welded note, how much are we specifying we're leaving out? We're trying to kind of leave it to them to do their job because it's not really, I'll call it structural, right? 200 pounds, I don't need much on that pipe weld to hold it, right? So by the time they seal it all up and caulk it, that should be enough. All right, not too bad, 17 minutes over. Questions? Lots of info and materials. I encourage getting all the Lincoln Electric books and reading them cover to cover if you're interested in this. Knowing about the processes and how they do things is cool. All those those base plate pictures that were up there a minute ago with all the gussets, I love those. I love looking through those. I love looking at those ideas. There's a couple of cool pictures in there where there's a dude welding a column that's like a 4-inch base plate to this monstrous beam. That's just super cool, dude. I mean, passes with that take, you know, the rest of his life. And any good welder, especially if they're doing stick, they burn a rod and then they burn a rod, right? 1 cigarette per burn. Yep. All right, cool. If you guys have projects or needs or issues or things, hit me up. I actually had my CWI back in the day, certified weld inspector. I've let it lapse because I didn't feel like doing the training and thing every 3 or 4 years or whatever it was. But it's a cool thing to do. If any of you guys are interested in it, we'd be willing to kind of help you with funding for it, or at least get your books and get through it. It's cool to know this kind of stuff when you're designing things, especially the one that hit me was how bad a weld could actually be and still pass. Because then I stopped designing welds to like factors of safety of 1.01. I started throwing in a lot more because I realized that they probably weren't giving me what I thought. Ruby? All right, everybody's beautiful.